Alright, so example 13 is similar to the previous one. We're going to start off with our diagram again. Luckily they've drawn a diagram for us both times. And we're starting by marking the tension on the string. Right, the tension is stopping them both from falling down. And of course we can mark in the weights. This time they've been kind enough to give us a 30 here, which is going to make a 60-degree angle there because you've got the right angle triangle that we're used to seeing. You've got the resultant force, which is coming off perpendicular again, as always. And then we just need to check the question to see if there's anything else going on. Do we have any friction? And what we're looking here is it a smooth surface or is it a rough surface? And actually, you see it's a smooth, fixed plane. So that tells you that there is no friction, which is brilliant because there's not going to be any resistance force. The other thing we want to notice is that it says show the acceleration of block B is 4/7 g. So it doesn't want us to get rid of the g and substitute for 9.8. It wants to leave our answers with the g in. So that's one thing we have to bear in mind while we do the question. So again, we need an idea of which way it's going to move. Hopefully again you can see that this is 5 kilograms straight down. It's going to pull this one up because this one is only 2 kilograms. So we'll make the positive direction straight down here. And the positive direction then has to match. They must have the same positive direction. So when this one goes down, this one goes up the slope. So then we resolve just like we did before. So the first way is to deal with the block by itself, the simple block to get started. So that's the 5 kilogram block in this case. And when we look at that, we should see that with force in the positive direction is the 5g. And it's just the tension in the string holding it back. And then do F equals ma with that. So 5g minus t equals 5 lots of a. And again, we've got two unknowns, just like the previous example. We've got the t and the a, and we're going to have to stop there. Okay, then we go and we get our other block and we examine that. So this time there's no friction, so it actually doesn't matter what R is. R is not going to come into it. We can just go straight in and we can resolve up the slope. Okay, so when we resolve up the slope for the 2 kilogram box, we start off by getting the force. So pulling it up is T in the positive direction because that's the direction I've just said is positive, going up to match with the down being positive there. And in the opposite direction, you've got the weight pulling it down. So this is minus, it's 2g, and we're going through the angle of 60, so it's cos 60. We then can do F equals ma, and we get that t minus 2g cos 60 must be equal to 2 lots of a. And that is our second simultaneous equation for this question. So all we have to do is rearrange and solve it. So I'll rearrange this one here. We've got t equals 2a plus 2g cos 60. And actually at this point it's worth working out what cos 60 actually is. So cos 60 is 1/2, so that simplifies to 2a plus 2g times 1/2, which is t equals 2a plus g. And all we have to do is substitute this t value into the equation that I have on my left here. So we pop that in, and this is 5g minus 2a plus g equals 5a. And then we've got 5g minus g goes down to 4g, minus 2a, add it to the other side is 7a. We divide it, and we get that a is 4g over 7 meters per second squared. And then we look back in the question and we pray that we've done it correctly, and we see yes. The acceleration of block B is 4/7 g, same as 4g over 7. Now it's a bit crafty here because it says block B, right? But obviously the acceleration of both blocks is the same, right? That's fundamental in these questions, that both blocks accelerate in the same way, which is why we can use the simultaneous equations. Part II asks you to find the tension in the string. So again, we're just going to take our value here and we're going to substitute in. So we then come back to here and we have that t is equal to 2 times acceleration, which is 4g over 7 plus g, and we might as well continue the theme and leave it in terms of g, and it'll give you 15g over 7 newtons, right? Because tension is always a force, so it's measured in newtons. So that's part A, right? All of that there. Now we just have to have a little look at part B. State you have used the fact that the string is inextensible in your calculations. So the inextensibility of the string, it means it's like not elastic, it's solid, it doesn't stretch at all. And that's always going to be the same effect that it has on the question. The effect is that if you imagine an elastic string, you would, as you pulled one, there might be a slight delay before the other moved. And you might get that sort of flick effect like you'd see with a catapult. So they wouldn't move necessarily at the same time. So what the inextensible string gives us is that the acceleration, which is very important, of the both objects is equal. Okay, so they move as one. As soon as one moves, the other must move in the identical manner because they are connected by this inextensible string. Finally, part C, another very common question just to finish us off, asks us about the tension that the pulley is experiencing. So if we think about the pulley, and I'll model it as a particle, draw a little diagram. This is the pulley here. And it's got two forces of T. It's got the straight down T, so it's feeling the drag of that T pulling it straight down, and it's got this T going back down the slope acting on it as well. And what we want to know is we want to know the magnitude, so that's the overall amount of force being exerted on it. And we can do this by resolving. So we first need to know what angle this is at, and if we consult our original diagram, we'll see that if this is 30 degrees up here, then it's going to create a Z angle with the tension here at the top. So this too is going to be 30 degrees, because that is parallel to the horizontal. So if we add that in, that would be that to the horizontal we've got a 30 there, which makes this angle in here 60. So it's 60 degrees between the two tensions. So if we were to resolve it, we would see that horizontally, if I go to the other way, so horizontally going to the left, there's only one thing pulling the pulley to the left, and it's this tension here, and it's going to be T, and then we're going through this 30 degree angle there to the horizontal, so it'll be T cos 30, which is going to be equal to 15g over 7 times root 3 over 2, which is 15 root 3 g all over 14. Okay, so that's just resolving this force, because it's the only force pulling the pulley to the left, and going through the angle of 30, so it's T cos 30, and substituting in from our calculator. Then we've got the downwards motion. So we've firstly got a whole T that's going straight down, and then we've got this T that's also pulling it down, but this is going to be T cos 60. Right, because we've gone through the angle to get to the horizontal of 60 degrees. So if we add them together, we'll get, cos 60 is 1/2, so we'll get 3 over 2 times T, which is 15g over 7. This is going to be 45g over 14. So I've now got I've found the horizontal and I've found the vertical amount, and if it's asking for the magnitude, I've broken it up into two parts, but then we need to put them back together to get the magnitude, and hopefully, as we know by now, to get the magnitude of a vector, we are going to use Pythagoras. So magnitude is the square root of all of this. Right, 15 root 3g over 14 squared plus 45g over 14 squared. So we pop all that into our calculator. You have to give me a moment here to do that. That is apparently 21 root 3 or 36.4 newtons to three significant figures. Okay, it's quite a different, interesting one that you've just got to think about what the string's doing. So the string is pulling it down and it's pulling it in that direction, both with tension T. That's what the pulley's feeling. The pulley's feeling that pressure of both of those things. So we just draw the diagram with the pulley and the two forces on it, and then we resolve it to the left. We resolve it straight down. Then we get the individual elements, and to find the magnitude, we square and add them together. And that is the end of Unit 7. So there's plenty of questions for you to do, right? If you have a look in exercise 7F, right, it's going to be a little bit challenging, obviously, with these connected particles. You've probably not seen these properly since year 12, but we'll have a go. You can have a go at all the questions there. You know, pick out the ones that look good, and have a go. A lot of them exam-based questions. So good luck with that.